So we didn't quite get to this in our lab lecture, so I'm glad we can actually just take the time to go over it here on a video. DEPT C13 NMR spectroscopy. It sounds like it's going to be complicated. Distortionless enhancement by polarization transfer. And the scariness of that description is quite complex. That is to say, how this technique is performed. Fortunately for you, even if we were live in person and our NMR was up and going, most of this stuff would probably be handled by our NMR tech, who's Caleb, as you saw in our video last semester. And so you don't really have to know the details and the deep physical chemistry of how this technique works. Once again, our goal here in organic chemistry is to understand that this technique exists and what data it provides. Now, I will give you at least a little brief idea about what happens. And that is, this is a technique that is able to use a series of radio pulses in a certain arrangement, and also polarization, which just means in three-dimensional space, the radio wave is kind of rotated at the plane of that wave in how it's oscillating in space relative to the other radio signals. And even myself, I'm not fully well versed in this technique's theory behind it. But the 90 and the 135 actually have to do with the angle at which the wave has been rotated in its polarization. And so the main idea that you need to walk away from this and be able to use this spectra and this technique is to know that when you perform a DEPT-90, for example, spectra, what it does is it takes your normal broadband decoupled C13 spectra and it alters it in the following way. For DEPT-90, what happens is all of the carbons that have 3 hydrogens and 2 hydrogens and no hydrogens disappear. So if that peak in your original decoupled C13 spectra, if any of those peaks are due to a carbon with anything but a single hydrogen on it, those signals will disappear. And so the only signal that remains in a DEPT-90 spectra are the carbon signals that are due to carbons that have 1 hydrogen on them. And because that kind of, now I know that those are due to single carbons that have 1 hydrogen on them. How does that help me? How does that help me narrow it down? DEPT-135 technique does the following. If the carbon signal is due to a carbon that has 3 hydrogens on it, or 1, the signal remains a positive signal. That is to say, it goes up from the baseline or from the x-axis. If that carbon is due to to a carbon that has 2 hydrogens on it, it's still the carbon giving off the signal. But if it's due to a carbon signal that has due to a carbon that has 2 hydrogens on it, then that peak or that signal will go negative. It'll dip down. It'll actually point down relative to the other peaks. And then lastly, if it's due to a carbon that has no hydrogens on it, in other words, it's due to a carbon that either has triple or double bonding and then everything else is carbons connected to it, there's no hydrogens on it at least, I should say, then it disappears. And so it sums up like this. In your broadband decoupled spectra, you'll have a bunch of peaks throughout the spectra. But you don't know what they are. You don't know, and you know they're carbons, but you don't know whether they're carbons with 3 hydrogen, whether they're carbons with 2 hydrogen, whether they're carbons with 1 hydrogen, or whether they're carbons that have no hydrogens on them. So you throw it into the NMR machine and set up 2 experiments, one that's a DEPT-90 and one that's a DEPT-135. And what it does is it gives you enough information to completely identify everything. Because any peak that is positive and found in the broadband decoupled and positive and found in the 135 DEPT but not in the 90, that will always be a CH3. Any carbon whose signal is in the broadband decoupled disappears in the 90 and is negative in the 135 has to be a CH2, because none of the other combinations match that. If it's a CH, you'll find that signal in your original C13, and you'll find it positive and present in the 90 and the 135 DEPT. And if it's a carbon that has no hydrogens, you'll find it in the broadband decoupled, but you'll find it absent in both the 90 and the 135. So first of all, when we look at the example on DEPT, there's some additional non-spectroscopy information that's been provided, and that is the chemical reaction that's being used here. And so what we have is an unknown compound, C7H12, that is undergoing a reaction with this borane, BH3THF, and this peroxide with NaOH. And when it does that, it transforms into a new molecule, C7H14O. And so this should be clear to you from what we learned back in Chapter 8 of OChem 1. We learned that borane, followed by this condition, which is an oxidative condition with peroxide and sodium hydroxide, this typically transforms alkenes into alcohols. So likely this C7H12 is an alkene, and this C7H14 has been transformed into an alcohol, and also the less substituted alcohol. Now, real quick, let's do a degree of unsaturation calculation. So there's 7 carbons, so that should be 16 H's if it's fully saturated. However, we have 12. And so that means we have 4 divided by 2. That's our degree of unsaturation. 16 minus 12, what we actually have, divided by 2, which is 4 divided by 2, is 2 degrees of unsaturation. Over here, we have C7H14, so we've got 16 minus 14 divided by 2, which would be 2 divided by 2, or in other words, 1 degree of unsaturation. So how do we take this? Well, what we should realize is in Chapter 9, we learned that while, yeah, there is a way to react borane with triple bonds and make enols that turn into aldehydes. We'll just have to keep that in mind. That's likely not what's going on here. But I don't know, maybe, because it could be alkyne, but let's just take a look at the structure. So could it be an alkyne transforming into an aldehyde? Let's rule that out right away. So if we go to our chemical shift chart for C13 NMR, we see that for alkynes, for carbons and alkynes, they typically are in the region of about 90 ppm to, I don't know, what's that, about 65, maybe 67 ppm. And we look at our data here, which we look at compound A, which is what is reacting with the borane. And we don't see any peaks that are in that region. In fact, what we do see is 2 peaks, 106.9 and 149.7 ppm. If we go to our C13 chemical shift chart and we look in that region, so that's about, you got 106 around here, and then 149, that's around here. So around this region right here. If we look up here, we got aromatic carbons. However, if you know what an aromatic carbon typically is, like benzene, if you drew the structure benzene, you realize that has 4 degrees of unsaturation. It can't be that. That can't be our molecule. So it's really got to be an alkene or alkyne. But if we look right here, we see, oh, okay, alkenes, even if it's a little bit outside of that, it's not quite 149, it does look like carbons. Now keep in mind, the carbon we're actually talking about causing the signal is, it's kind of hard to see. It's slight different color. You can kind of see. Let me move. Yeah, see how it's because of the lighting. It's kind of grayer than the regular carbon atom. And so that's this right here. So this is the carbon causing this signal. This is the carbon causing this signal. In other words, when the carbon is near other carbons that's in the double bond, it kind of shifts it downfield. Whereas if it's near hydrogens, it tends to shift it a little bit upfield to lower ppm. And that probably is what we're doing here. Because remember, let me show you again. The compound, we've got a 150 and we've got like a 106. Let's see. Yeah, we got about a 150 and a 106. And so we probably have an alkene with a CH2, and then we've got an alkene carbon that's got two other carbons connected to it because it's on the far side. So that's probably what we've got. But let's double check it using the DEPT analysis. So what do we observe here? Well, what we should be observing is in a problem like this, where we're using DEPT, we have to identify where the peaks are the same and where they're missing in our 90 and our 135. What we just want to see is in the 135, we have these two the same, these two the same, and these two the same, and these the same. And so remember, and then none of them show up in the 90. So I don't know if you remember that, but what we just showed in the video prior to this is if something shows up in the broadband decoupled, not in the 90, but negative in the 135, and that's what these are the negative peaks, that means they're all CH2. Now mind you, keep in mind, this CH2 doesn't have to be a single bonded carbon. It can be a carbon with two H's and then something bonded on each side of the carbon singly. So another carbon atom maybe on each, or a chlorine, whatever, or oxygen, doesn't really matter what, it's just not a hydrogen. But it can also be a C double bond C, or I should say a carbon double bonded to something, not hydrogen, and then two H's. More often than not, it's a carbon, because if it's an oxygen, then that's the end of the molecule and it'd be formaldehyde. But so probably a carbon. So according to DEPT, as we just said, these carbons all have CH2s connected to it, whereas this one, it's absent in both the 90 and in the 135. And if you remember from our chart, which is in your textbook also, according to that chart, when you have something that disappears from both of the DEPT spectra, then it is a carbon that has no hydrogens on it. No hydrogens. So we need a carbon that has no hydrogens on it. And if you think about it, that is what a carbon that would be connected to two carbons would be. So this is likely our structure, at least part of it. We have a CH2, oh, not in B though. We have a CH2 double bonded to a C that's connected to two C's. And then what do we have? We have three other signals, and only three signals. Remember, that's another clue that you get from C13. How many total signals do we have? We have 1, 2, 3, 4, 5. We only have 5. We're missing 2. There's got to be some symmetry. Either one of these peaks represents 3 carbons, or there's 2 peaks that represent 2 carbons, and then a third peak that just represents 1. And I don't know if you've realized this, but one way that you can get a lot of symmetry like that, where you've got multiple shared peaks, one way to get a good mirror of a plane of symmetry in a molecule is by ring structures. So if you think about that, and then also we ruled out the alkynes, so that 2 degrees of unsaturation that we talked about right here for C7H12, it can't be alkyne because we already showed, based on the chemical shift of our C13 spectra, there cannot be an alkyne carbon. It has to be an alkene. So that other degree of unsaturation has to be due to a ring. Now, you could say, well, Dr. Rice, maybe it's due to another alkene, but if there was another alkene present, then we would have seen 2 of these electrophilic addition reactions. We would have seen 2 oxygens and H's added, and we would have got a compound that was C7H5O2, because it would have happened twice. So more than likely, this is 1 alkene and 1 ring in our structure, because the ring, which does create a degree of unsaturation, does not react with these reagents. So likely this is a cyclic alkene. Doesn't have to mean the alkene is in the cyclic structure, but just simply there's a ring and an alkene. I guess I could say ring. And it's an alcohol, and the ring would still be there. And look at our structure for compound B. Once again, it's got 1, 2, 3, 4, 5 compounds. And what we've done is these have mostly stayed the same as those up there. However, these 2 peaks have dropped a little bit in their chemical shift. And that's because likely these are the 2 carbons that were the double bonded carbons. They've now become sp3 carbons. Why are they still a little on the high side? Well, if you think about it, you've added an OH. And alcohols, or carbons that are next to alcohols, are in that region of about 50, 60. It probably can be a little lower the farther you get away. In other words, these are carbons directly connected to an oxygen that has an H, to an oxygen. That's in this region. But a carbon that's 2 carbons away from an O is going to still be upfield, but a little bit over. It's going to, the farther away the carbon gets from the O, the farther it's going to shift back upfield. And that even kind of seems to grow exponentially. Like, it happens quickly. Once you move 2 carbons away, it really almost just goes back to normal. It doesn't even sense the oxygen. So likely we've turned into this. And I think about it, we know what our BH3 does. It adds an OH. It adds an OH to the least substituted carbon, and then the H to the more substituted carbon. So now we've got this. Let's see if that bears out. Remember, this carbon used to be no H's. Now it's 1H. And if it has 1H on it, it should show up in both the 90, the 135, and the regular broadband decoupled spectra. And what do you know? The peak 40.5 shows up in the 90 and shows up in the 135 DEPT as a positive peak. And when it does that, shows up in the 90 and the 135 and the broadband decoupled, all positive, that is a CH. And that's what we got here. What about these 3 peaks? Which are probably these peaks right here still, just slightly changed, because there was a change in the structure. Well, they don't show up in the 90 still, and they still show up in the 135. Nothing really changed with them. So they're still CH2s. These 3 peaks are still CH2s. So how do we have 3 signals from CH2s plus some of these structures? In fact, we know these are just 1. How do we know these are just 1? Because we've already kind of deduced what that structure is. So we've got 3 more signals that are CH2s, but some of them are more than 1 carbon. There's some symmetry. Anyways, as I was kind of hinting at, what you kind of learn is that, you kind of learn is one way to get good symmetry is by having rings. And so if you draw this structure, CH2, 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 CH2. And because of symmetry, which would go like this, then what we have is these 2 carbons are the same, these 2 carbons are the same as each other, and this carbon is by itself. More than likely, these 2 carbons that are directly connected to the sp2 carbon are probably what caused the 35.7 ppm peak. These two that are a little bit farther away are probably the 28.7, and this one is the 26.8. Now, I don't really make you label. That's not really part of the assignment, but it does help you kind of, finally narrow down and say, oh, okay, I think I know what's going on here. This is the 149.7, and this right here is the 106.9. And then over here, this is likely the 68.2 because it's directly connected to an oxygen. This one is probably the 40.5, and nothing else has changed in the ring structure because that's not, BH3 THF doesn't do anything to these sp3 carbons with H's on it. It doesn't react with them, so they remain the same. More than likely, because these are 3 away from oxygen, but they're still closer than these ones are, so these are probably the 29.9, and then these are probably the 26.9 and the 26.1. But once again, these are the same as this. These two carbons are the same as each other. So that's it. We analyze these two unknown structures based on chemical data as well as C13 data, but combined with DEPT-90 and 135 spectra, which helps you narrow down what type of carbon, and by type I should say whether the carbon has 3, 2, 1, or none, or no hydrogens. Hope this clarifies, gets you ready, because there is a problem very similar to this on the worksheet, and more than likely we'll develop another problem like this that you'll find on the lab practical. Sorry again about the long lecture, but I'm glad that we all decided it'd be better just to have this put into video form for you to watch later. Hope this was helpful. If you have any questions still, feel free to email me, stop by office hours, or any kind of time, maybe next week after we talk about the video lab experiment, you can continue to ask me questions about the worksheet for spectroscopy. Goodbye.